Hi, welcome to this talk on best practices for secret management with GitOps. I'm Marck, I work at CloudBees. Secret management is an issue across software development. And in this talk, we are looking at it within the context of GitOps and Kubernetes. We'll be discussing some of the aims of secret management, some secret management strategies with GitOps and Kubernetes, what trade-offs they present, as well as various secret management tools that can help. First, let's go over some of our terms and set the context in which we're considering this problem of secret management. So why Git? It really doesn't have to be Git, but Git is the most widely used version control system in the software industry today. GitOps uses Git as a single source of truth for declarative infrastructure and enables developers to manage infrastructure with the same Git-based workflows they use to manage a code base. This means all infrastructure configuration and application code are stored in Git repositories. Infrastructure as code isn't unique to GitOps, but it is foundational for GitOps. With GitOps, the entire state of your system is declaratively described in Git. As a result, all application definitions, configurations, and environments are declarative and version controlled. This means all changes to your system are observable and verifiable. Benefits include application deployment and lifecycle management being automated and auditable. So how do we manage secrets with GitOps? As we don't want to have them exposed in Git. We're going to focus on a GitOps workflow while deploying to Kubernetes. You can do GitOps without Kubernetes, but a GitOps approach works very well with Kubernetes. In fact, Weaveworks, who coined the term GitOps, describes GitOps as an operating model for Kubernetes. GitOps is a great way to do Kubernetes cluster management and application delivery. A Kubernetes operator can be used to poll your Git repos for changes and automate Kubernetes deployments to match the actual state of your system with the desired state as described in Git. When doing GitOps with Kubernetes, it is helpful to have a GitOps Kubernetes operator, which automatically ensures that the state of your cluster matches the config in Git. The operator polls the Git repo for changes or divergence between the desired and actual state and triggers deployments in Kubernetes. It makes sure your new container images and config changes are propagated to the cluster. Flux, Argo CD, and Jenkins X, for example, all have Kubernetes controller that ensures the state of the cluster matches the config in Git. And GitOps tools will also be able to monitor for configuration drift and issue alerts, or course correct themselves. So there'll be remediation. And the state of your system will match what is declared in Git. So now that we have a sense of GitOps as an operational model for Kubernetes, let's consider the issue of secret management. Applications can hold quite a lot of sensitive information. So what exactly do we mean by secrets? Secrets are anything that might grant you authentication to a system or authorization to a system. Therefore, secrets that have these privileges are things we want to carefully manage. Some examples include username and password, DB credentials, TLS certificates, and API tokens. Secret is anything used for authentication, enables you to log into your system and authenticate, or can be used for authorization, that is to prove identity, as with TLS certificates. By secrets, we are referring to things that grant additional access and capabilities, including to potentially sensitive information. This information that your application has access to is anything that is confidential. And this includes credit cards, email, etc. These are things we would like to keep confidential, but don't necessarily grant additional access to other parts of your system. Secret management is really about managing credentials. And we need to deliver secrets to our end applications. As we adopt the tools that enable us to enrich our orchestration, deployment, or automation, such as Kubernetes, we face an interesting challenge. How do our applications get all the credentials they need? In general, when we refer to secrets, we're referring to access and authentication tokens. Okay. A secret management process prevents access to authentication tokens from being compromised, and this is very important. Kubernetes does provide a built-in object for managing secrets called a secret. We'll go over quickly what that is, a Kubernetes secret is. In your cluster, secret information can be stored in a protected resource object, the Kubernetes secret. And the secret object is convenient to use. It provides a declarative API that makes it easy for application pods to access secret data without any special code. However, these secrets are base64 encoded and not encrypted. Fortunately, in Kubernetes, you can opt into encryption at rest by enabling this feature. The Kubernetes API encrypts the secrets. Optionally, you can use an external key management system, or KMS, before storing them then at CD. So far so good. We have a way to store sensitive files, such as certificates, inside the cluster, and we can protect those secrets at rest with a suitable encryption provider. However, secrets that you load into the cluster must exist somewhere. What do we do? Do we keep a copy or rely on Kubernetes to be the only source of truth? And how do we back them up? These kind of questions will immediately arise, and secret management systems help us with those questions and many more. Secret management systems exist to deliver secrets to our applications. How do our applications get all the credentials that they need? We need to be able to load secrets into the cluster safely and securely. After all, the secrets are created externally and then migrated to the cluster. And we need to keep a single and trusted source of truth for our secrets, so we don't risk having our secrets out of sync. And we need a full audit history of who changed the secrets and for what reason. We want to understand who has been using the secrets, who has access to them, and in most cases, we want a story about how we can periodically rotate them. You want your secret management system to be able to answer all those questions. Let's take a look at some of the ways to do secret management with GitOps and Kubernetes. We have a limited number of choices of type of choices. So we'll go over two main types of choices, either using encrypted secrets or an external secret management system. But within both types, there are many variations and tools that implement the basic flow. So first, encrypted secrets. And these enable you to put your secrets in Git because they will be fully encrypted. The idea is that you can encrypt your secrets into a sealed secret, which is safe to store even in public repos as it is encrypted. Sealed secrets are often stored in your repos along with the application code and infrastructure config. And examples include Bitnami sealed secrets and Helm secrets, and we'll look at both. We have a couple of benefits from this, such as you get a free full audit history for free from Git, and you can reuse the same merging strategy that you use for your application code and your infrastructure changes. And your code and secrets are kept in sync, which is nice. So sealed secrets has a controller, or encrypted secrets, they have a controller which generates a public and a private key. Once you have the public key, you can encrypt all your secrets using it. And then storing the public key and the secrets in the repository is perfectly safe, even if the repo is public, as the public key is used only for encryption. The private key is kept in the sealed secrets controller and is used to decrypt the values and create a standard Kubernetes secret. It's a cryptographic system that uses pairs of keys like this with public keys, which may be known to others, and private keys, which may never be known to anyone except the owner, in this case, the controller. This is called asymmetric encryption. Effective security requires keeping the private key private, but the public key can be openly distributed without compromising security. This means that you can store your secure credentials directly in configuration files in Git, share your Git repository with anyone and everyone who needs access to it, and yet none of those users have access to your credentials. Your chief security risk, as you can imagine with this situation, is that your private key of the pair becomes known. The private key needs to be very well protected, as anyone with access to that key has the ability to decrypt and gain access to secret information in the manifest. And we'll look at an example of one implementation which enables you to, which provides one safeguard for your private keys. So Helm secrets are another way to store encrypted secrets in Git. The underlying mechanism to secure secrets is similar to sealed secrets, but with some noteworthy differences. First, it enables you to leverage Helm to template secret resources. And if you're already using Helm, you may find it more convenient than sealed secrets. Another significant difference is that Helm secret is using the popular open source project SOPS, which stands for Secret Operations, and is developed by Mozilla for encrypting secrets. SOPs support external key management systems like Cloud Provider Key Management Systems, or KMS, making it more secure as it's a lot harder to compromise your keys. However, Helm secrets are strongly coupled to Helm, so it is more work for you if you were to decide to switch to another templating mechanism, such as Customize. You can also use this pattern of SOPs plus key management systems without using Helm secrets. SOPs can be used independently of Helm secrets. It's a good tool for encrypting files in formats such as YAML and JSON and ENV. Once you encrypt these files containing secret information, you can keep the files in Git with the rest of your application and infrastructure code. In order to decrypt the file, SOPs needs the correct keys. As with the previous example, it pairs well with all the major cloud provider key management services to control access to the required keys to decrypt the files. Our next category, secret management tools that we'll look into, is the external secret management system. And examples here include Vault or the major cloud provider secret stores and key management systems that they have. External secret management systems generally do quite a lot for you and do so securely. They come with many capabilities and to some extent can be replicated with, and these capabilities can be replicated with encrypted secrets, but that will leave you with much more work to do as the end user. So if your needs are more limited, then encrypted secrets plus KMS may fill all your secret management needs. However, for more complicated use cases with multiple platforms and multiple use cases for using the actual secrets, an external secret management system may better fit your needs and be more helpful. So these external secret management systems may differ in features, but the general principles are the same. In this talk, we will largely discuss Vault, but again, the cloud provider secret management services offer similar functionality. These external secret management, like GCP, for example, are another way that we can externalize our secrets configuration. In this case, secrets are not stored in Git. You only have a pointer to the secret, and that pointer is stored in Git. However, they provide a way to securely store and manage your secrets. They give you, quite often, identity-based access to sensitive information and data encryption in flight and at rest. There are some hard questions in secret management, which we continually have to keep in mind, and are, since we are dealing with more complicated use case, are more appropriate for this section as our standards may very well be higher. So, number one is quite standard. How do we get secrets into our applications, and how those secrets then are updated, and how our secrets are revoked, and how do we audit who is using our secrets and accessing them? And then in addition, what do we do in the event of a compromise? First, to get a sense of how these will be approached, let's go over the goals of an external secret management system. One of the goals, of course, is to reduce or eliminate secret sprawl. It gives you one central location for your secrets. They're all kept, for example, in Vault. And Vault promises that they are going to encrypt everything. So both at rest inside your secrets vault, as well as in transit between Vault and any of the clients that want to access it, and that have the appropriate credentials to do so. So at least if you could see where the secret is stored at rest in Vault, it is encrypted. So even if you access those secrets, you do not get implicit access to all the secrets therein because they are all encrypted. In addition to that, Vault gives a fine-grained access overlay, so ACL, on top of this, so that you can say the web server needs access to the database credential, the API server needs access to the API tokens, but everyone or every service does not need access to everything. So it can be very service-based. And then on top of this, we have an audit trail. We can see what credentials the web server accessed, or for example, car accessed. So we have much more visibility and control over how these things are being managed. And also, if we believe that something was compromised, it can help us in securing that situation. So step one is we move away from secret sprawl to a centralized location for our secrets, with strong guarantees that the secrets are encrypted at rest and in transit, and strong guarantees around who has access with visibility into what is happening so we can have an audit trail. The challenge is applications do themselves a terrible job of keeping secrets. So they can often log secrets and log their credentials out to, for example, a logging system, or when there are errors, they can log them out in diagnostic output. For example, username and password can show up in an error report. And this includes when shipping to an external monitoring system. In general, applications do a poor job of keeping secrets secret. And it is best to simply acknowledge this fact and to realize that even though we are securing location, we are encrypting them, and we're controlling access to the secrets in their centralized vault location. This is not enough. We also need to have dynamic secrets. And by that, we mean secrets that are ephemeral and short-lived and on a regular basis are rotated, and these are moving targets. So if any secret is accidentally leaked or logged, it will only be around for a very short time. And you can provide the time frame for that. So you can keep it quite short. You can give it 30 days, however you like. You add a bounded time. And this is a moving target for attackers. So it makes it harder for them, one, to grab the secrets, but also use them to their fullest potential if they should come across a secret. But secret rotation is hard, and it's harder when using encrypted secrets. An external secret management system will handle this automatically for you, improving your security by providing a moving target, by essentially making the secrets moving targets for any attackers, any would-be attackers. In addition, your external secret store should control access to secrets and encryption keys. It does this by enabling fine-grained authorization of which users and applications or services are permitted to access these secrets and keys. So many external secret systems, such as Vault, enable creating a credential unique to each client. For example, if you have 50 web servers, each one will have its own credentials. They will not be shared amongst them, which means that if one is compromised, not all 50 are. It also enables you to pinpoint which one is compromised, shut that one down, rotate its secrets, investigate what happened, and spin the web server back up. And this will not bring your system down or pause your maintenance or anything. So your blast radius when you have a compromise is lower. When you have secrets and credentials given for each instance of a service, which is great. External secret management systems, they solve three main challenges. They help eliminate secret sprawl. They govern secret access through identity and access management, and they can help you with securely storing your sensitive but not necessarily secret data by offering services such as encryption at rest, because doing encryption well is quite difficult. So it's nice to have that automated and sort of done for you in a very secure way. There are, however, some issues that people run into with running Vault. For example, you do actually have to run a Vault server. And in addition to that, it is not, sometimes it happens that individuals are essentially logged out of their Vault instance. And this really is a first key issue. So when Vault encrypts its data, it also encrypts its own secrets to decode that data. This asks the question of how does Vault decrypt the secrets when they are needed? You need to unseal the Vault. Basically, there's a master key to the kingdom, in that if you have the key, you would just go and unseal all the secrets if it was available to an attacker. And this would entirely break through your defense system, all the service or access control lists that you've put in place, all the encryption, all of that would be undone. So the answer is that you don't give out this key to just anyone. However, sometimes users have been known to be locked out of the Vault and need logging back in basically to a Vault instance. So to summarize, we have some desirable attributes for secret management, and we want our secrets to be encrypted at rest and in transit, and we want them only decrypted in memory. We want access control. We want rotation, revocation, and audit logging for our secrets. Ultimately, though, our first primary problem revolves around getting secrets to the code that needs it without anybody else getting to see their secrets. Let's think about how we get secrets into a running container with an external secret store. how do we inject those secrets into apps while they are running? The external secret managers externalize your secret configuration, and we need to get that decrypted and into your cluster. In this case, secrets are not stored in Git with external secret management systems. Actually, a reference to the secret is stored in Git, and like a pointer to the secret. So when you're using an external secret store, it is the responsibility of the application to retrieve the secrets from the store securely. Sometimes teams develop custom solutions for accessing their secret data. And the result of this, especially because these solutions need to be quite secure, is often overlapping efforts and quite a good rate of efforts because they need to be done well. So it may be more helpful and secure to use an open source tool such as Kubernetes External Secrets, which was open sourced by GoDaddy. And you can see a diagram in the slide on Jenkins's use of external secrets. Or you could use something like Kubernetes Secret Store CSI driver. And so this integrates secret stores with Kubernetes via a container storage interface or CSI volume. The Secret Store CSI driver allows Kubernetes to mount multiple secrets, keys, and certs stored in enterprise-grade external secret stores into their pods as a volume. Once the volume is attached, the data is mounted into a container's file system. And using the Kubernetes Secret Store driver allows you to easily configure your cluster to pull the secrets from your external secret store manager. And that plays nicely with GitOps mentality and workflow, because you still store everything in your Git repository. For example, you're storing the pointer to the secrets, but the actual secrets are themselves externalized. But you are still achieving your goal of having Git as your source of truth. That being said, there's a lot of innovation in the space and in secret management tools in general. So many cloud providers, as well as Vault, have their own helper tools for this. If you choose to externalize your secrets and use an external secret store, you would basically not use Kubernetes. You would either consume them directly from your application or library, or an SDK such as GoDaddy's external secrets, or you would leverage the CSI driver that basically maps the secrets from Secret Manager into a file system or an in-memory virtual file system so that your applications can read their secrets from disk. I've only touched on a few secret management solutions and of two broad types. There are many other secret management solutions, gives you sense, and there's even more. There are pros and cons to every secret management solution. Ultimately, the right secret management solution depends on your needs and your use cases. But we do hope that the summary of some of the tools available and some of the workflows and enumerating their pros and cons can help you choose the one that is best for your systems. Thank you. And now if you have any questions, please feel free to ask.